Hello, everyone. Welcome to the 30th session of the GO2NE Global Ocean Oxygen Network webinar series. I'm Guizhi Wang from the State K Laboratory of Marine Environmental Science and the College of the Ocean and Earth Sciences at Xiamen University in China. The whole GO2NE team is very happy that you took the time with us and incredible speakers this morning, afternoon, or evening. Before starting, there are a couple of announcements. Firstly, please look out for the first edition of Good News in the near future. Good News will be a newsletter that highlights the work of Good and GO2NE. Secondly, the next GO2NE webinar will be planned for the 13th of July. So please look out for details to register for the next webinar. Further, here are some housekeeping announcements. You as attendee have the possibility to type your questions in the question box. The chat can be used for sharing additional information, or if you have any logistical problems. If you want to speak at one of the upcoming webinars, please submit an abstract. And the link is also shown in the chat box. But let's start. We have two great scientists speaking today. We'll start with Yangyang Zhao, who will present for 20 minutes, followed by 10 minutes Q&A. And afterwards, Esther Portela will be giving insights into her latest science for 20 minutes, also to be followed by 10 minutes Q&A. Now, Yangyang Zhao is an assistant research scientist from the State K Laboratory of Marine Environmental Science at Xiamen University in China. He is going to talk about interactive hypoxia acidification in coastal waters, response to climate ocean warming. Yangyang, the floor is yours.
Great, thanks, Guizhi, for the introduction, and welcome everyone, and good evening. I'm Yangyang Zhao, and from the College of the Ocean and Earth Science, and also State K Laboratory of Marine Environmental Science of Xiamen University in China. I defended my thesis 2 months ago, co-advised by Dr. Binghan Dai from Xiamen University and Dr. Nicholas Gruber from ETH Zurich. My research interest is on the deoxygenation, acidification, and the global climate change. So today, you will be hearing about the hypoxia and acidification, and I'm going to tell you a little bit about their interactions and how it is respond to the ocean warming. First, I'll give you a brief introduction to the hypoxia, ocean acidification, and ocean warming. So what happens to the ocean when carbon dioxide emission increase? Since the industrial evolution, the carbon dioxide emission from the fossil fuel burning and the land use change remains about a half remains in the atmosphere. It warms up the planet, and about 90% of the heat and the additional heat is absorbed by the ocean, and so the ocean is also warming up. The warming up of the ocean has reduced the solubility of oxygen in the seawater and reduced the ventilation of the deep ocean, and as well as enhance the biological metabolism. So through this way, the the oxygen in the ocean has lost by about 2% over the past 5 decades. On the other side, the other half of the emitted carbon dioxide goes into the land and the ocean. Once the CO2 goes to the ocean and it reacts with the seawater to release the protons and reducing the pH and turning the ocean sour. It threatening the growth and survival of the carriers organisms such as the coral reefs and mussels, and by reducing the saturation state of the calcium carbonate. So we know now that the warming, oceanification, and the deoxygenation can individually impact the organisms and the ecosystems to a varying degree. And largely unknown is the impact of the compound events, especially with feedbacks from the ocean circulation and the climate. Of the global oceans, and in the eastern tropical Pacific and the high latitude, the world are largely affected by the warming and acidification. But at the 200 meters, in the low latitude regions and also in the subpolar Pacific, severe affected by the compound events. The dynamic coastal ocean is also the hotspot of the compound events, and the direct human perturbations make it more complex and challenging to resolve their impacts. And the oxygen loss in the ocean is not only manifest in the oxygen minimum zones with their expansion, but also with the rise in the size and the intensity of hypoxia in the coastal waters, as shown in the red dots in the map. The hypoxia is usually commonly defined as the concentration of the dissolved oxygen is smaller than 2 micromole per liter, and since the 1960s, more than 500 of hypoxia sites have been observed, and with a total hypoxia area about 250,000 square kilometers. The hypoxia in the coastal water is mainly driven by the increasing nutrient import to the coastal waters, and the nutrients stimulate the growth of the phytoplankton to producing the organic matter sinking down to the bottom layers. And the microbial respiration of the organic matter then not only consumes the oxygen, but also release the carbon dioxide and to release the protons. The right figure shows that the pH decrease over the oxygen decline at the present, and also the pre-industrial and the future scenarios. And we see that the pH decrease during the oxygen depletion is triple of the pH decrease by the invasion of the atmosphere carbon dioxide. Also, we little know about how it's affected by the ocean warmings. So comparing the colder western water of the American and also the warmer waters in the Gulf of Mexico and the Philippines and its corals, found that the pH decrease in warmer waters is slower, but the saturation state of the calcium carbonate and omega in the warmer waters is decreasing faster with the oxygen decline. So to a more complex, our question is how with the oxygen with the increasing carbon dioxide in the atmosphere, how the interaction of the hypoxia and ocean acidification will respond to the ocean warming in the eutrophic coastal waters. And to tackle this question, we select 4 regions, and the Yangyang estuary, Peru estuary, and northern Gulf of Mexico, and also the Chesapeake Bay. And contrast to the other 3 regions, the Chesapeake Bay is a semi-enclosed regions with the constrained water exchange with the open ocean, and these 4 regions both severe effect by the human predations, and the hypoxia is frequently observed in these regions in the wet seasons, and the hypoxia area can reach up over 20,000 square kilometers of the Yangyang estuary, and also in the northern Gulf of Mexico. So we plot the sample data in the subsurface water with depth more than 10 meters, and we can see that there are clear decline trend of the pH and also omegas with oxygen decline and with oxygen depletion, but in the Peru estuary, Yangyang estuary, and the northern Gulf of Mexico, and they show the similar almost the linear trend with oxygen decline. But in the Chesapeake Bay, it's much more complex. So today I will focus on the 3 regions of the Peru estuary, Yangyang estuary, and the northern Gulf of Mexico to explore their interaction of the hypoxia and the acidification. The aerobic respiration of the organic matter is thought to be the major driver of the enhancement of acidification in the coastal waters. During the aerobic respiration of organic matter, consume 1 mole of organic matter will consume the 138 mole of oxygen, and then produce 106 more of DIC, but reduce the total air by 17 moles. So we simulated the pH decrease from the oxygen with oxygen from the saturated state to 0, and we can see that the sample dose are located between between 2 lines. One line is for the surface water, for the subsurface waters with the borderlines, and also the surface waters, the thin lines. We know. So we here can see that the pH for the specific oxygen concentrations, the pH also variations can contribute by the water mass mixing. In this sense, the water mass mixing between the surface water and the subsurface water largely decouples the acidification to the hypoxia. And the below 2 figures is plotted the pH against the DO at the in situ temperature, and we can see, even though this, we can see that the samples dot are some outside of these 2 lines. So other processes may contribute to the outliers, the pH variations. Previous study in the North Gulf of Mexico, Wang has revealed that the additional pH decline in the bottom waters contribute to the upward transport of the basic flux of the DIC and the total air current. And also in the Chesapeake Bay, Chai also found that the sulfate reduction and the dissolution of the calcium carbonate contribute to the pH variations. But in the future scenario for the warming, we know that by the end of this century, the CO2 levels can increase to more than 1,100 ppm, and the temperature will increase by 3.3 to 5.7 degrees. So in here we choose the CO2 level of 1,135 ppm, and the temperature increased by 4.5 degrees to simulate how the hypoxia and the oxygen respond to the ocean warming. First, we model simulated the oxygen acidification made by the warming, and we can see that without warming, the increasing of the atmospheric CO2 levels will decrease the pH by 0.4 units and decrease the omega by 1.6 units. But with warming effect, there will be largely mitigate. There are two ways. The first way is the direct thermal effect. This enhances the hydrolysis of carbon dioxide and the dissolution of the bicarbonate. This results in the decrease of the pH, but the omega is increased. Another effect is the indirect DIC effect. This reduces the solubility of the carbon dioxide in seawater. This effect increases both the pH and omega. So overall, the pH and the warming effect these two effects offset each other to result a little change in the pH, but the omega can be increased 0.3 units. Further, during the oxygen in the future scenarios, during the oxygen decline, we can see that the atmospheric CO2 increasing result in the pH decrease by 0.4 units, and this is smaller than that the pH decrease during the oxygen depletion. And also we can see that in the future scenarios, without warming, the pH decrease during the oxygen depletion is enhanced by 0.13 units due to the weakened buffer capacity. But with warming effect, we can see that the pH decrease during the oxygen depletion can reduce by 0.05 units, and also we found that the reduced solubility of the CO2 and oxygen play a little role in the pH decrease. Overall, the warming can mitigate the pH decrease by 0.06 at oxygen depletion of the total pH decrease by 0.552. In contrast, for the omega, we can see that the reduced solubility of the oxygen, carbon dioxide and oxygen can increase the omega by 0.3 units, and the overall effect is that the omega is increased by 0.14 of the 0.84. But this is in the ideal conditions, and not always the oxygen in the systems can be depleted. In more reality, the hypoxia formation is constrained by the solubility of oxygen in seawater, the water residence time, the supply of organic matter, and the oxygen consumption rate. And how the solubility of the oxygen in seawater can be predictable. And in the previous tree, we assume that the water residence time is about 10 days. We assume that in the future scenarios, the organic matter supply is also enough, but the oxygen consumption rate is increased from 15 to 20 micromole oxygen per kilometer per day and using a Q time of 2. So we can see that compared to the present scenarios in the future, the pH decrease during the oxygen depletion can increase by 0.24, and this can lead to the oxygen level approaching the 0 within the water residence time. For the calcium carbonate, for the omega, it's also same, but during the oxygen depletion and within the water residence time, the omega decrease can increase by 0.14. Even so, to summary up, the direct thermal effect and the indirect DIC effect act synergistically on mitigating the omega decrease caused by the atmospheric CO2 forcing, while offset each other on pH decrease. And in the future, with the ocean warming, the pH decrease is enhanced while the omega decrease is mitigated during oxygen decline within the water residence time. In the future, I will further work on the cascading effect of the hypoxia and all the acidification under the ocean warming, such as the denitrification, ocean acidification on the carbon to nitrogen ratio of the organic matter, and also the calcium carbonate dissolution. So that's all my talk, and thanks for your attention.
Okay, thanks, Yangyang. And now we have 2 questions in box. The first question is, on average, at which depth we can find hypoxia? Okay, now in most coast areas, such as the Yangyang Strait, Peruvian Strait, northern Gulf of Mexico, and they are usually in their depth is about 20 to 30 meters. And in some enclosed basins in the coastal waters, they can be very, the depth can be very large, because the hypoxia formation is happened because of the constrained water exchange between the open oceans. Okay, the second question is acidification the cause of hypoxia?
I think the acidification is concurrent with the hypoxia, because the micro respiration of organic matter it consumes oxygen. At the same time, it produces the carbon dioxide. So the acidification is enhanced. The acidification is enhanced with the development of the hypoxia in coastal waters.
The third question is, to what extent hypoxia affects marine biota?
Oh, the hypoxia is usually defined that about 2 micromole per liter. This threshold means that under this oxygen levels, the marine organisms will be affected. But now I also found that read that the oxygen the hypoxia is for almost all marine organisms will be pose a negative impact through its life stage, or for different kinds of the marine organisms. But to what degree I'm not focused on this part, so I cannot tell you to a certain intensity the hypoxia can, but I can tell you that it play a negative impact on the marine organisms.
Okay, the next question is, do we have different scenario if we are considering coastal situation without oxygen production with ecosystems?
I think in my study, I also just take the business as usual, the scenario, an example to illustrate how the hypoxia and also ocean acidification interaction and respond to ocean warming. I think now with more human effort into to reduce the CO2 emission and the different scenario can happen, and maybe in the future the increase of the CO2 levels or the warming will be much mitigated. But still production in the ecosystem, that's maybe mostly in the surface layers, but in the bottom layers, because the water exchange is constrained by the strong and by the stratification. So
Okay, next question. In case of the high ventilation rate in marginal seas, can we talk about hypoxia?
Yeah. The higher ventilation rate in the marginal seas, the hypoxia will maybe cannot happen because the formation of the hypoxia depends on the oxygen supply and against the oxygen consumption. If the oxygen supply by the ventilation rate is larger than the oxygen consumption, so the hypoxia cannot be happen.
Next is, could you please comment on the seasonal dynamic of hypoxia in these regions?
Okay, in these regions, the hypoxia, why the hypoxia is mostly occurred in the wet seasons, or because the hypoxia formation depends on two factors. One is that the strong stratification or the slow exchange, the strong stratification which limits the oxygen supply from the surface layers, and in these systems, in the summer or in the wet seasons, the large amount of fresh water from the rivers can discharge into the coastal water. They can form the strong stratification, and also the high loading of the nutrients can stimulate the production of the organic matter, which is also very important for the hypoxia formation in the bottom waters in these coastal waters. But in the winter or in the dry seasons, the strong wind will destroy the stratification and to supply the oxygen into the bottom waters. So the hypoxia usually cannot form in this in the winter or in the dry seasons.
We still have more questions, but our time is up. So we have to move on to our next speaker. Yangyang, please stop sharing your screen. Our next speaker is Esther Portela. She is a research associate from Institute for Marine and Antarctic Studies at the University of Tasmania in Australia. Her talk is on physical mechanisms driving oxygen uptake by the ocean interior. Esther, the floor is yours.
Thank you very much. So I'm sharing my screen. Can you see my screen?
Yes.
Yes, okay. So thank you very much. I'm, as it was just said, I'm a research associate at the University of Tasmania. And at the same time, I keep my affiliation at LOPS in France. So I'm going to talk today about two different studies that I did in the frame of my collaboration with LOPS in France on the physical mechanisms driving oxygen uptake. This work I did in collaboration with the several authors that you will see through the presentation. So the motivation of the study is that, as everybody knows, that the ocean is losing oxygen. It has been observed over the past decades, as we can see here in this figure, in the red colors. We can see that most of the ocean is losing oxygen, but it's not only that the oxygen is being lost, but also the models are predicting that this tendency is gonna keep and even increase over the next century. So this oxygen loss has been attributed to the ocean warming that acts in different ways on the oxygen concentration. So it acts directly by decreasing the oxygen solubility, which has direct impact on the oxygen concentration. It also increases the respiration rates, which also decreases the oxygen concentration. And more indirectly, it also increases the stratification of the water column, which has an effect in decreasing the ocean ventilation, meaning that it decreases the rate at which the oxygen is being is crossing the mixed layer base, and also the rate at which oxygen is transported in the ocean interior. So in these two studies that I'm going to present today, I will focus more in this part. So the mechanisms that are driving this oxygen uptake, and the question is exactly which are those mechanisms. So the this first study. To address this question, what we did was compute the oxygen subduction, defined as the flux of oxygen from the mixed layer into the ocean interior. So we have this schematic here that shows the main mechanisms. So the equation to compute this was to divide the processes into the kinematic processes and the diffusive processes. So the kinematic processes are the lateral induction, which is represented by an arrow with an U here, and is given by mixed layer gradients and strong currents that transports oxygen through the mixed layer base. The similar process is the eddy-induced subduction, but is driven by the eddy velocity. And then we have the vertical subduction, which is mainly wind-driven, like by the Egmont pumping. At the same time, we have the diffusive subduction, which is composed by the vertical and the horizontal terms, and it's more this diffusion on the base of the mixed layer. And then we also have these biogeochemical sources and sinks, but we are not taking those into account now because we are focusing on the physical mechanisms. So I will talk first about this diffusive oxygen subduction. This is a term that is often neglected in the computations of oxygen subduction because it's not easy to take into account. So the way we did this here is, so we separated the vertical and the lateral components, and they are given by a diffusivity coefficient. This is the vertical one and the lateral one. So in the case of the vertical diffusivity coefficient, what we did was to have a spatially variable coefficient that is computed from the internal tide. So we have to keep in mind that this is a lower bound of this diffusivity because we are not taking into account the other processes that are important at the base of the mixed layer. But at least we have a realistic spatial distribution, which is kind of an improvement from most of the estimations. So here we have the map. We can see that it's mainly positive because, of course, the oxygen concentration is usually at saturation in the mixed layer, and the flux is towards the ocean interior. And then in the bottom panel, we have the lateral oxygen diffusion, which in this case, we couldn't have a geographically variable diffusivity constant, so coefficient. So we have a constant value of this value. And then to compute, to have a sensibility test, I repeated the same computation with an upper and a lower bound. So we compute the total oxygen subduction to consider the variations of this term. So now I'm showing here the kinematic terms, which are in the top row. So lateral induction, eddy induced, and vertical velocity. And in the bottom, I have this total oxygen subduction. So first, we will focus on the lateral induction. We can see that we have hotspots of oxygen uptake, the red colors, and release, so the blue colors, that are concentrated in the North Atlantic and Southern Ocean mainly, because they are the places with the deepest mixed layer and strong currents. So we can see that the lateral induction is quite like shaping the total oxygen subduction. But when we integrate globally, we see that this contribution is negative. So it's not contributing to the oxygen uptake into the ocean interior, but rather the opposite. If we move to that induced term, and this is actually, I put a question mark here because it's a very uncertain term. Actually, I forgot to say that this study was carried out with by using the echo reanalysis for the physical variables and the World Ocean Atlas for the oxygen data. So in the echo reanalysis, we took the bolus velocity, but it's a parameterization. So this is a first order estimation of the induced term, which is kind of noisy, which is expected, and it is the most important in the Southern Ocean and in North Atlantic. And then if we move to the vertical velocity, we see that it's very weak, but it's homogeneously constant in the subtropical gyres. So we can see that the subtropical gyres are uptaking oxygen. And if we integrate globally, we see that this term is one that contributes the most to the global oxygen uptake. And then we add this diffusive term that I showed before. So we can see here that even if this is mainly positive, but with our computation, this term, the diffusive term, accounts for 21% of the total subduction. But if we take into account the range of the lower and the upper bound computations, it ranges from 10 to 64%. What it means is that now we couldn't estimate with certainty this term, but it's potentially very important, and it needs to be constrained much better than it is now if we would want to refine this computation of oxygen uptake. The next thing we did was to carry out isopycnal decomposition by ocean basins. So I have here in different lines, different ocean basins and density level. So I am only going to highlight here the subtropical mud waters that are in the first squares, and then the subpolar and subantarctic mud waters that are like denser squares. And we have the different contribution of the different terms. But we can see that, as I showed before, the subantarctic and subpolar mud waters that are in the Southern Ocean and the North Atlantic are like accounting for most of the oxygen uptake in a short range of isopycnals. And then the subtropical mud waters that are formed in the subtropical gyres are spread over a range of isopycnals, and it's weaker but consistently positive and dominated by vertical velocity. So in order to account more for the role of mud waters in the oxygen uptake and its key importance, I'm showing here this map from Tallinn, and you can see the formation regions of all the mud waters around the ocean. So to the right in these bars, I computed the total oxygen uptake by ocean basin in gray, and then the green bar is showing the oxygen uptake by mud water. So it means that I only consider the region and the density ranges where mud waters are formed. And we can see that this contribution of the mud waters. Particularly, one of the key findings of the study is that up to 70% of the global oxygen uptake occurs during mud water formation, which takes place only over 35% of the outcropping surface. So it means that it doubles its efficiency as oxygen uptake. And it also indicates that mud waters need to be very well defined and constrained in models if we want to estimate correctly this oxygen uptake by the global ocean. We also found that global oxygen uptake exhibits important regional variability, and different regions are dominated by different subduction mechanisms. And also that oxygen diffusion is locally small, but it likely plays a key role in the global integral. So it needs to be very well defined, much better than it's now. So the second study I'm going to talk about today is on the same line of this previous study, but now we are focusing in a region of important oxygen subduction, which is here in the North Atlantic, particularly in the Yangyang Sea. So this is a paper that's already in revision from Poche and collaborators. And so it's focusing in this region. You can see here, I'm showing the mean oxygen concentration and at the mean depth of the Labrador seawater. So Labrador seawater is a mud water that is either formed locally in the Yangyang Sea here, or also advected from the other formation region, which is the Labrador Sea, the other side of the Greenland, of Greenland. And this water mass, because it's a mud water and it's ventilated the deep ocean, plays a key role for climate, and it transfers surface water properties and tracers of atmospheric origin into the ocean interior. So heat, carbon, oxygen, and other traces. So that's why this it plays a key role for climate. So what we did here was to collect an extensive oxygen database in the region. So the region is here constrained by bathymetry in the Inland Sea. So we have hydrographic sections in this section here. It's repeated hydrography between 1991 and 2018 in combination with Argo data from 2010 to 2018. The definition of the Labrador Sea water was made by an uncommon criterion, which is a layer thickness criterion. So it's based in the feature that this is a mud water, so it's characterized by having low potential vorticity and it being thick. So it forms thick layers, and we are following the maximum thickness. And so this water must change in density over time. And we can see it here in the hydrographic sections, how it becomes lighter and denser, and then also in the Argo data. And finally, what we did was also oxygen decomposition in two different terms. So for one side, the oxygen concentration at saturation, which is like the maximum oxygen that water mass at a certain temperature and salinity can absorb. And also, and the difference between this and the oxygen, that the stored oxygen is the apparent oxygen utilization, the AOU, that gives is like a proxy of the mixing and the biological consumption. So I'm showing you here the hydrographic sections, and those provide long-term variability, so a long-time series, but low temporal resolution. We have most of data every 2 years and with some gaps. Most of them are taken sample in summer. So the periods of strong convection are not represented very well here, but we still can see the Labrador Sea water that we are following. We have salinity, temperature, oxygen, and AOU, and we can see the internal variability, which is quite strong. We see that at the beginning and the end of time series, so we are calling those P1 and P3. We have a higher oxygen concentration, which is accompanied by fresher and colder waters, and a decrease in the AOU. And in the middle of the time series, we have lower oxygen concentration and warmer and saltier waters. If we add the Argo data over the Argo period, which is between 2010 and 2018, now we have a very detailed temporal resolution, so high temporal resolution, and we can see other events like jets of strong convection, like this here, for example, that is oxygenating the Labrador Sea layer, water layer. And then we have also strong oxygenation in the end of time series, so from 2016 to 2018. And this strong oxygenation is accompanied again by lower salinity and lower temperature and a decrease in the AOU. So now what we are interested in is more to follow why is this happening. So the causes, the dynamical causes of this variability. So now for this, we are following the oxygen properties of the Labrador Sea water here. In gray, in black dots, this is the hydrographic sections, and the black lines are the hydrographic, the Argo data for observed oxygen, and then in red, we have the oxygen at saturation. But to this oxygen at saturation, we already subtracted at 7%, which is a mean value of the under saturation that we can find in these deep convection regions as the Labrador Sea. So the difference between the black and the red is the AOU. So the first thing that we can see here is two periods, like two different behaviors, like period 1 and period 3, as I said before, with different characteristics. In P1 and P3, we have a high oxygen concentration and close to saturation, and the opposite happens in period 2. And also we can see that there's no significant trend over the almost 30-year record, but mostly is dominated by a strong internal 2-decade variability, and that this variability of the observed oxygen concentration is mainly driven by solubility changes. No, it's mainly driven by AOU-related processes, which explain more than 2/3 of the variability, and only less than 1/3 is related to solubility changes. So now we are interested about the dynamics of the subpolar gyre, which we can see here with the arrows, because the Irminger Sea is surrounded by the subpolar gyre. And as I am schematizing here in this figure, the state of the gyre can induce a stronger convection. And when we have strong convection, we renew the water mass and we oxygenate it. So we are linking this state of the gyre with the observed oxygen properties. So first, we computed over the Argo period, the mixed layer depth and the mixed layer temperature, which is the temperature is this line. We see that by the end of the period, when we have a high oxygen concentration, the convection was deep and the water was cold. And in panel B, I'm showing the North Atlantic oscillation. So it's also a proxy of the atmospheric conditions. And then in the last one is some different computations related to the gyre intensity. So we have the wind stress curl in bars and the relative vorticity in these horizontal lines, average over a 5-year period, and also the sea level anomaly. So we see first that in period 1 and period 3, we have positive NO, meaning that we have an intense gyre, we have strong winds with a strong wind stress curl and colder water. And in the period 2, so from 2002 to 2014, when oxygen concentration was lower, we have negative North Atlantic oscillation, weak subtropical gyre, weaker wind, and warmer water. So what we can conclude here is that we have this interannual to multi-decadal variability. And so in the periods of high oxygen concentration, we have deep convection, which is not new. This is something that is very related. And we have little AOU, but the AOU that we find is explained by mixing during the convection period. So we have well oxygenated waters in the mixed layer that it's mixing strongly with the waters below. So the waters below are less oxygenated, and this mixing between the two of them is creating this apparent oxygen utilization. In contrast, during the shallow convection period, so period 2, we have low oxygen concentration, and the AOU is higher, and it's explained mainly by the horizontal advection, so the transport from the Labrador Sea that increases the age of the water. So in summary, this study provided that a recent provided information about recent average oxygenation in the Irminger Sea over the last 2-3 years. And the updated oxygen time series show that we don't have a linear trend over the past 30 years, so we need longer records to detect such a thing. And we have a strong interannual to decadal variability dominated by changes in AOU-related processes, such as vertical mixing and lateral advection. And thank you for the attention. And I would like to thank my collaborators. And if you want to know more about this subject, here you have 2 references. The second one, we hope to have it published soon. So thank you very much again.
Thank you, Esther. And now we have one question here. I wonder how to define different bounds when calculating without oxygen loss.
Different bounds when calculating oxygen loss. I don't understand the question. Sorry. Can the person that asked the question explain more? The bounds, when I talked about bounds, was not about oxygen loss, was about diffusive oxygen subduction. I don't know if it's related to that. Can Clarence explain better? Please.
Clarence, can you clarify your question? Clarence 10.
No, okay. Well, how to define different bounds? No, I'm sorry. I don't understand the question. I don't know what that doesn't mean. Because I am not, confusing that.
Is that when you setting up your equations, you have some like range of? I guess the question.
It was here when I computed the upper and lower bound. So it was not about oxygen loss at all. It was just about computing the oxygen diffusion. So we just changed the value of this diffusivity constant in order to provide a range of possible values, because this computation is uncertain and it's not it's a bit useless to provide a concrete value that is not going to represent reality. So rather we chose to provide a range between the lower and the upper bound found in the literature. So we took the most known value, which is like 1,000, and then we took 1 and more order of magnitude 2 in order to account for the range that is like possible, even if we can't know, because it's a very complicated thing to compute. So the result of this was what I showed here, like our contribution to the diffusion term changed from 10 to 64. If we consider the lower and the upper bound for the diffusion term. If that was the question.
Okay, the next is oxygen concentration or solubility changed seasonally or in summer or winter?
I don't know, read the question. Oxygen concentration will change seasonally. Yes, well, oxygen solubility changes with temperature. So sure, in places where temperature oscillates, oxygen solubility too. And in the case, so in the first study, we realized it's a mean state, so we are considering the mean, but the deepest mixed layers are in winter. It's what we considered, so it's mainly winter state. And for the time series I showed in the second study, we have, of course, summer and winter changes. They are strong, but actually the formation of this Labrador seawater occurs in late winter when we have deep convection. So it's mostly when this mud water is formed. And yes, it depends on, the solubility depends a lot on temperature, so on season.
Okay, the next question. Oh, can you read it? Is that?
Yeah, I can read it. So the tax of oxygen is decreasing in seawater. If the question is if it's the same case in the coast. So yeah, well, in general, yeah. As the previous speaker showed, this very well-known map of hypoxic coastal places. Unfortunately, the measurements are not spread all over the world, but in the places where they are taken, mainly they are decreasing, yes. But different processes act in the coast, so it's not that simple sometimes. My work is more open ocean. From my work, I can't tell if the question went in that sense, but other studies address this.
Okay. As a marine chemist, I have a question related to the marine chemistry. Where you see the AOU decrease or increase, do you have related dissolved inorganic carbon measured, or does it show some relation with your AOU data?
So where exactly?
Dissolved inorganic carbon. Dissolved inorganic carbon. Do you have data?
Of
DIC.
inorganic carbon? Yeah, no,
Yeah.
I'm not looking at that at all. I'm just looking at oxygen.
Okay. Yeah.
Some colleagues of mine are looking at carbon in the same region in the Labrador Sea here in Labs where I am now, but I'm just looking at oxygen transport. But the similar studies are being carried out now on carbon, but it's not my field.
Okay, just curious. Thank you. And here is another one. rate is done in marine waters. Is this the case for coastal waters?
That's the previous question I translated from French.
Oh, okay. Okay, thank you. So do we have more questions? Okay, thanks.
Thank you.
Yeah.
So if anybody has more questions or want to write an email, I'm happy to answer.
And thank you again for your active participation. And we're looking forward to welcome you again in July for the next session of the webinar. And the exact date and topic will be announced shortly. Have a nice day. Thank you all.